Gothenburg, Sweden, and I will be the moderator and the interviewer at this live broadcast, where I will have the privilege of interviewing 2000 Nobel, from year 2000 Nobel laureate Arvid Carlsson, who was the one who first, for example, discovered the transmitter role of dopamine in the brain. And that will also be the topic of today's discussion, the history of dopamine. This educational web seminar will be brought to you by a company called LabRoots, which is a leading scientific social networking website and provider of scientific virtual events such as this one. They have asked me to provide you with some practical instructions before we start, which are the following. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. We'll try to answer as many questions as we can. You can enlarge the slide window by clicking on the screen icon in the lower right-hand corner of the slide window. If you have any technical problem viewing or hearing this presentation, please click on the support button at the top right of your presentation window, or submit your problem through the green Q&A button lower left. This is an educational webinar and thus offers free continuing education credits. After the webinar is over, please click on the CE button located in the bottom left-hand corner of your web page and follow the process of obtaining your credits. So, with these introductory words and instructions, I would like to say hello and welcome to Arvid Carlsson, who will today share his view on dopamine, both with respect to historical aspects and with respect to current problems and prospects. And hello, Arvid.
Hello.
Nice to see you here.
Pleasure.
I thought we should start with a brief history lesson, and I think this would be the appropriate place to start. This is the late 50s, this is Bethesda, and this guy is Bernard Brodie. Could you please tell us about him?
When I met him, I was kind of astonished, as a matter of fact, because I expected him to be like the other professors, academic professors of my home university, Lund, Sweden. And here I met another type of person. He described himself as a gambler, very little academic, and he started out. He was actually born in Liverpool, but he, as a child, when he was a child, the family moved to Canada, and he went to school, and he started a career in boxing, and a successful career. And for some reason that I cannot go into details here, he made a decision to switch into what? Into organic chemistry. I think he is the only person in the world who switched from boxing to organic chemistry. And from there, he went on into pharmacology, and in pharmacology he became a pioneer in a very special modern, at that time very modern kind of pharmacology, chemical pharmacology. That is pharmacology that, rather than traditionally where you base yourself on physiology, now you base yourself on chemistry. So the important thing in chemical pharmacology is to do chemical analysis to more precisely find out where does the drug go, where does it fix itself, what kind of chemical changes will there be. So his lab, the lab of chemical pharmacology at the National Institutes of Health, was I think on the absolute top of modern chemical pharmacology, and I was enormously successful to be able to be accepted there as a visiting scientist in 1955, and got, and what another thing, very fortunate for me, was that just a few months before I came there, they had made a fundamental discovery, and that was that if you give an antipsychotic drug called Recibió, very much used in those days, and if you inject that into an animal and then analyze for a chemical in the brain that was one knew very little about, but there were lots of speculations about this chemical, was serotonin. And if you inject Recibió into an animal and analyze for serotonin, you will be astonished to find serotonin has gone altogether. And so that started out some very interesting new research. And I was fortunate enough when I came there to get to go right into this research and do some chemical analysis on serotonin in blood platelets. So that is how it started.
Do you think that Brody has been sufficiently recognized? Should he have had the Nobel Prize, for example, do you think?
Well, the problem was that he opened up an entirely new field. And if you go to the Testament of Nobel, it's very specifically said that the prize should be given for a specific discovery.
Yeah.
And sometimes the committee, they don't take that so seriously, but sometimes they do.
Okay.
And in this case, they did take it seriously, so he didn't get it.
Okay.
But he had his pupils and visiting scientists like myself got prizes, and very, very prestigious prizes. And he got lots of prizes himself, but not the Nobel Prize. But there were two of his pupils who got it. I was one of them. The other one was Axelrod, Julius Axelrod.
Yeah. Okay, so you just spent half a year or so as a postdoc here, and then you went back to this building, and this is not Gothenburg. This is Lund.
This is the place where the Department of Pharmacology of the University of Lund was located in those days. Now it's used for very different other purposes. So that's where when I started out to study medicine, and I was accepted there by the professor to become a young scientist, amanuensis as it was called, and I did some work in classical physiological, pharmacological work, but also with a touch of chemistry. My professor was he wanted me to go into chemistry. He actually guided me into chemistry, I must say. So, so I started out in a very different field, in dealing with bone metabolism and using something brand new at that time, radioactive isotopes, the possibility to measure quantitatively. So, and my thesis then dealt with that. But then later on, my professors told me that maybe this calcium metabolism and bone isn't really in the core of pharmacology. Maybe you should do something else. So, and I thought I better do what they said. So I got through some very good friends of mine, and they helped me to get in touch with Brody's lab. So that is how. But now, after having done those 5 months, I came back, and this, of course, from now on, I was a serotonin man, very much. Okay. But not quite serotonin, because I got the idea that maybe serotonin is not the only thing you should look at. There are some closely related compounds in the brain that are they are chemically related, but they are not indolamines, they are catecholamines, but they seem to have functions that are similar, and in the periphery these compounds were very important, adrenaline and noradrenaline. So, and I thought maybe one should just to see, does reserpine work on the catecholamines? So that...
If I just may interrupt here, at this time, was serotonin recognized as a brain neurotransmitter?
No. I think that Brody probably, he thought of it in terms of being some kind of transmitter, but in those days there was no evidence really. Okay. And there was no evidence for that matter that in the brain the catecholamines could be neurotransmitters either.
Okay.
So, in the brain itself. They could be in the nerves surrounding the brain, but not in the brain.
But was chemical neurotransmission in the brain accepted at this time?
No, not
even that.
It was not accepted at all.
Okay. Okay.
So I got started, and I had learned something very well. First of all, I was enormously fortunate because the man in the whole world who would be the best one to start to collaborate with was Nils Åke Hillarp. And where was he located? Well, at the University of Lund. Very, very strange phenomenon. And this man, he had done some very fundamental work on the adrenal medulla. He had been able to localize that organelle in the adrenal medulla where adrenaline is stored. He called them granules. They could also be sometimes they're called vesicles. And so he had done some very fundamental work on that. So he was right in the middle of research, the kind of research where I wanted to go into. And he had a methodology and everything. So I wrote to him already when I was in the US and asked him, would he like to collaborate with me? And he said yes. Mm-hmm. So as soon as I got home, we started more or less immediately to do work. And within a few months, we had done the experiment. So we had given reserpine to rabbits and found that the adrenaline that he could analyze in the adrenal medulla had gone. Wasn't very little left. So that was a good start, I can say.
Understand it. Before going further, the background of all these slides, of course, we wouldn't have had that without Hillarp.
Yes, that was a little later. That we started out with this very good technology, but rather primitive technology that was needed to do the experiments showing reserpine acting on adrenaline. But as this work proceeded, there became a need to really locate not only in the adrenal medulla but also in the peripheral nerves and in the brain to locate these amines. And what you see here, the green color, is the result of a chemical reaction that Hillarp and his colleagues invented that could visualize in the fluorescence microscope the amines, serotonin, noradrenaline, adrenaline, could be visualized in the electron in the fluorescence microscope. Later on, also in the electron, but in the fluorescence microscope. So that was a dramatic step forward. So that's why we have this background.
Yeah, exactly. Then you, when you came home, wrote 2 very important papers, but I guess you couldn't have done that without the right equipment. And could you please tell us something about this thing?
That was another fortunate thing, because it so happened that in Brody's lab, they were developing an entirely new revolutionary technique to measure in very low amounts by chemical assays rather than previously only in bioassays. By chemical assays, you could precisely identify and analyze a number of important compounds, some of them endogenous, such as the amines we are talking about, others, of course, also drugs. And this instrument, which was the prototype, I was working on a prototype, but that later on became by Aminco, this instrument company, constructed to become this instrument that we see here. And it revolutionized for example, the analysis of endogenous compounds that previously one could not have analyzed before, but then by means of using fluorescence rather than light absorption, you could gain 1 or 2 orders of magnitude. All of a sudden, you were down to concentrations that were beyond reach before. Okay. So this was a fantastic instrument. And the first thing I did when I arrived back home was that I ordered such an instrument.
Of course.
I didn't have the money, but I ordered it, and that's a good way to get started. So I had to raise the money, and I was fortunate in being able to raise the money.
I mentioned 2 papers, and this is one of them on the presence of dopamine in brain. Could you first comment upon this one, and then we will come back to the research in Rabbit's paper later on.
Yes, yes, this paper used, well, for reasons that we will come back to, I became interested in dopamine. Dopamine is another catecholamine, but not of any interest to pharmacologists in those days, because it was considered to be an inactive compound, perhaps and probably a precursor to the synthesis of adrenaline and noradrenaline and adrenaline, but otherwise not interesting. But for reasons that we will come back to, we developed a method to analyze dopamine in the brain, in tissues in general and in the brain, and found it's there. And it's there in amounts that are at the same level of noradrenaline. So what we actually said, even in this first description of our method and the results, a very short paper in Science, we said, in view of these levels that we have, it's not, we must consider the possibility that dopamine is not just a precursor. It is an agonist in its own right. Okay. So that was an important paper from that point of view, certainly.
And now we will have some evidence for that assumption. And first, you have already mentioned reserpine. This is just to show the plant from which reserpine is obtained, from the root of this Rauwolfia plant. And of course, it was used first in India, but then in Western countries for the treatment of both psychosis and high blood pressure. And you discussed already Brody's experiments with this compound. What you did in this experiment was the first definite evidence for dopamine being a transmitter, wasn't it?
Yes. Our simple reasoning was that if possibly important compound, if it disappears, it could be actually leading to a deficiency, something that didn't occur to Brody, because for some reason he thought it was the other way around. We had to skip that. But we simply said, okay, Here we had a condition where we have a deficiency in noradrenaline, because noradrenaline was what we had analyzed in the brain and found to be important. So what could we do in order to test the hypothesis that here we have a deficiency of noradrenaline? Well, we couldn't give noradrenaline so easily into the brain because there is a blood-brain barrier, so it didn't get in. But there is a precursor, an amino acid, and this precursor, for that precursor, there is a transport mechanism across the blood-brain barrier, and inside there is an enzyme that could convert the amino acid into, finally, noradrenaline. That was what our thinking. So, okay, so we gave, we had these reserpine-treated animals. They were, you will soon see a picture of that. They were on the one on top here. You see they are, they have very, very severe disturbance of their movements and very low wakefulness. You could put them in places, as we did with these two rabbits, and very similar positions, and they remained there. So they were very severe motoric disturbance and very low wakefulness. And then we injected intravenously dopa, this precursor, this amino acid precursor, into the rabbits, and within 15 minutes you have the same two rabbits and now they're up and running. The most astonishing result.
You must have been amazed when it happened.
Yes.
Do you recall
really.
it? Do you recall the day?
Oh, yeah, yes. Well, yes, we were. Well, it came on not quite as astonishing because we started out with mice.
Okay.
And in mice, we couldn't see, of course, they started to move, no doubt. But in the rabbit, we could see so much more.
Okay.
So, well, in any event, it was we were just as excited as the rabbits, I can tell you.
And then you measured the transmitters in the brains of these animals. You measured noradrenaline.
Yes, and we were so disappointed because in spite of this effect, there was still no noradrenaline in the brain. So that's why we asked ourselves, because we could conclude from the data that we had that it has to be an amine that is doing this. And the one that immediately occurred to us was, of course, the intermediate between dopa and noradrenaline, dopamine.
Of course.
And even though dopamine was recognized as a very uninteresting compound, we thought we must develop a method to measure it. Yeah. And we saw that science paper already, and also described in that paper is that not only that dopamine occurs in the brain, but also when we give reserpine, also dopamine disappears, and we could easily see that was a clear-cut connection between the occurrence, the reappearance of dopamine in the brain, and the behavioral response. So it became so obvious that what we see here is dopamine, an effect of dopamine, no doubt.
Perfect. And that, of course, paved the way later on to the treatment of this disorder, Parkinson's disease. Did it occur to you at once that this could have implications for Parkinson's when you saw these rabbits, or was that just later on? I
must confess, at the time we did that experiment with L-dopa, we didn't even know that a Parkinsonism-like side effect occurs after treatment with reserpine. Oh, now you are running through the slides very quickly, I can see.
I don't know what is happening now. We have a small technical problem, I think. We have come into my computer here. Sorry for this small problem. We lost the connection to the... It suddenly came into my computer instead. Okay,
yes.
We are back again. Thank you.
So that's something we learned at about the same time, that reserpine, one of the most serious side effects of reserpine is a condition closely similar to the disorder, Parkinson's disease. So that was one important piece in the puzzle. Then also we found other things. We found that dopamine, when they analyzed the distribution of dopamine within the brain, we found dopamine occurs is at especially high concentrations in the basal ganglia, and there had been lots of speculations that maybe there is something wrong in the basal ganglia in Parkinson's disease. It has something to do with movement. Nobody knew what it was, but so we had different pieces of the puzzle. So therefore we proposed that a deficiency, if you produce a deficiency in dopamine, that will lead to the full syndrome of Parkinson's disease. Okay. That was we postulated in 1959.
And then came Hornikiewicz showing
yes,
that this was the case.
That happened. But in the meantime, in 1960, when we published our, and also went to a meeting in London and published and reported our data that I have talked about already, the experts in the field said, no, dopamine couldn't be of any importance. But this study by Hornikiewicz helped at least to see that there could be something in something important in this, because what he found was that if you analyze brains post-mortem of Parkinson patients, these brains are depleted, very seriously depleted with dopamine. Yeah. So that helped.
And so then, of course, giving your rabbits a natural logical treatment here would be dopa, and shortly thereafter Kotsias introduced that treatment. But you were into testing dopa in Gothenburg as well, weren't you? Before Kotsias...
yeah, well, I went to a neurologist, a very famous neurosurgeon, as a matter of fact, in Lund, and proposed that we should collaborate on this interesting new thing. He was not at all interested. And of course, who could think in those days that a little chemical, such a small molecule, could do, the deficiency in that could lead to this very complex syndrome of Parkinson's disease. That was too far-fetched for anybody to believe in.
Okay.
Yes.
Okay, we must go on here because time goes, and of course, dopa became the first line of treatment for Parkinson and still is, many decades later, first line of treatment for Parkinson's disease. I would just like to briefly comment upon this on-off problem and how do you think this could be managed as you regard it today?
Yeah, if you look at the left-hand picture, that's the early phase after you start, and as we did, and we could see ourselves. So shortly after Kotsias, we started out in Gothenburg and found that when we give L-dopa to Parkinson patients, the whole symptomatology improves dramatically, and they have, if one is careful with the side effects, they could be managed to have a relatively mild side effects. So this is the picture that you have on the left. If you look at the picture on the right, Unfortunately, after a number of years, for a quite variable number of years, you get very serious fluctuations in the motility with very disturbing involuntary movements. So, and what the reason for this we don't understand fully, but at least there is one thing that has become rather clear nowadays, recently, is that if one avoids these dramatic fluctuations in the concentration of dopa and dopamine in the body that each dose is giving, if one could convert that into a more stable administration, such as in the so-called duodopa, one can avoid a lot of this problem. So that was important, and this is where I feel the field is moving now in that direction, in a very interesting way. So we can probably get rid of a lot of the problems of the fluctuations.
And maybe it could even be that if you never expose the patient to this sudden high concentrations, if you start with a continuous administration beforehand, you can have a better outcome in the long term.
Yes, very mild, even administration. You will have much better results than patients have nowadays.
Okay. So the dopa story is still evolving. That's nice.
Oh, right, absolutely.
Now we'll turn to another condition, and that is schizophrenia and psychosis. And this is, of course, in 1952, when the Levodopa accidentally demonstrated the antipsychotic effect of chlorpromazine after Henri Laborie had made experiments with this drug, the surgeon Laborie. And at this moment, of course, no one knew the mechanism of action of chlorpromazine as an antipsychotic. Shortly thereafter, this gentleman, Paul Janssen, developed another antipsychotic drug that is haloperidol. You knew Paul Janssen, of course?
Oh yes, he was an extremely proficient person. He was an organic chemist. His father started a small company, drug pharmaceutical company, and he, as a chemist, he started to synthesize an enormous number of very interesting compounds. And not only was he a good chemist, he could also develop a good test lab that could test whatever kind of actions these drugs had. And not only that, he could also bring them to the bedside. And all this could happen just in a few years. He was very well known in Belgium, and he could get drugs on the market in a very short time. And perhaps the most spectacular of his many spectacular products was haloperidol, Haldol, which was doing the same thing as chlorpromazine, but much more specifically and powerfully. So haloperidol has later become very important in the development of antipsychotic drugs, as you say.
And as far as I understood it, people then realized that since reserpine decreases dopamine levels, maybe chlorpromazine and haloperidol do the same, and that was tested, and it didn't do the same. And then you did this experiment. That was reserpine again. We are now going to this famous 1963 paper. And what did you do differently here as compared to other people?
Yes, it was a simple reasoning. I thought that because chlorpromazine did not cause any depletion of any of these amines that reserpine does. And yet it causes a symptomatology in animals and a therapeutic effect that's very similar. Reserpine and chlorpromazine are very similar. So how could that be? Then I got the idea that maybe there is some feedback mechanism involved. So we had already postulated that there could be some receptors for these amines, and maybe what could happen is that when we give reserpine, when we give chlorpromazine, rather getting a depletion, we could get the opposite. We could get a stimulation. And why could there be a stimulation? Well, that is to overcome a blockade of receptors. So that was the idea, and it turned out this actually happened.
But this was before even the concept of receptors in brain was established. So it was quite a bold and brave speculation, wasn't it?
Yes, yes, people thought so, but I thought it was sound reasoning. Okay. But others felt they were so amazed, and they continued to be amazed for many years. Yeah. And there has been lots of historical discussions about how this came about. Yeah. But that was how we thought, and it turned out to be right.
And it was published in a fairly humble journal and a modest journal, and then it was not cited for some years, and then it was a citation classic.
Yes, yes. And
subsequently.
Yes, and that is something I actually, in those days, this idea of publishing in prestigious journals was not nobody thought like that before. So it so happened that some of our papers, a couple of others have been, one in Nature and one in Science, not because we were aiming at something prestigious. It just so happened they were journals just like others. So here we had another journal.
It was a sounder time, one might say.
Yes.
We are, in fact, running out of time somewhat, so we will hurry up here for a moment. And this is just the kind of model you draw up at that time. This is from the 60s, 70s, when your vision of the synapse at that time. And do you still think this is valid?
Yes, it's interesting that perhaps we shouldn't, since we are short of time, we shouldn't go into the different processes that are. You have this big circle in the middle here. That is a transection of the monoaminergic nerve terminal. It could be one storing dopamine or noradrenaline or serotonin, but in principle you have the same thing. You have a precursor, amino acids getting in. You have enzymes that convert the compound into the transmitter in question. You have storage granules, that store the transmitter, and then it is released by the nerve impulse to reach the target cell, the big cell you have on the right there, and it's on that cell that you have a receptor. So here we have all this was described in 1965, and I think one can say we have no reason to change anything. Perhaps we can be more precise, because here we have put in COMT that should be located in the target cell. That's not look at the catechol-methyltransferase. But otherwise, there's nothing wrong in it.
Okay. Then I would just like to mention that subsequently, of course, the dopamine blocking effect of the antipsychotics was confirmed by Snyder, for example, and Kreis in radioligand binding studies, and also then in PET studies in humans by Fard and others. I think we can skip this one. You did in fact support the dopamine hypothesis by a study with the dopamine synthesis inhibitor, clinical studies conducted here in Gothenburg. And then of course, coming to the pathophysiology of dopamine, there are in fact studies today indicating that there is increased dopamine release in schizophrenia. This is by Laruelle and co-workers. Do you think that this is part of the pathophysiology today of schizophrenia, that we have too much dopamine in the striatum?
It's more complicated.
Yeah.
We have areas where there is an increased release of dopamine, as demonstrated here in the basal under certain conditions in schizophrenia, but in other parts, and perhaps in the cerebral cortex, there could, as a matter of fact, be the opposite. So it's a very complicated situation that we have. Dopamine is not functioning well, that's for sure.
That's for sure.
But exactly how, it's more complicated.
Okay. And then, of course, dopamine is not working in isolation, and you have drawn up various networks wherever there is, for example, an important role of glutamate. This is one such scheme.
Yeah, this is a way of demonstrating the sites where psychotomimetic drugs act and through which neurotransmitters they act. And we have an interaction between the cerebral cortex and subcortical structures in the basal ganglia, in the brainstem, and so forth. And this is the first kind of attempt to put down a scheme for this complex interaction leading to psychosis.
Okay. Okay, then would you like to say something about the mystery of clozapine? What would be your, clozapine, as everyone knows, is an atypical antipsychotic without much of the traditional antipsychotic drugs' motor side effects, and some benefit also from the perspective of efficacy. What is your pet idea today regarding the atypical profile of clozapine?
It can be best illustrated by means of our drug OSU 6162, because I think it is doing the same thing as OSU 6162, although not so well.
Yeah, we will come back to that,
yes,
because we have some slides about that.
It's John the Baptist before Jesus.
Okay, we'll come back to that drug, similar drug later on. But first, a few words about partial agonists, because here you have also made an important contribution. This is just to illustrate the concept of partial agonists, that you have an agonist that blocks the effect of an endogenous agonist but causes a milder activation than a full agonist. And you thought that this might be a way to treat schizophrenia. Why did you think that?
Yes, we thought that a partial agonist, that was our initial thinking, a partial agonist is a mixed agonist-antagonist. So in other words, if you have a condition such as schizophrenia, where there is too much dopamine in certain places released, if you give a partial agonist, it should displace dopamine and thereby causing a decrease in to alleviate psychosis. That was the simple thinking we had to pose in the beginning. Later on, when the autoreceptors came in, it became more complicated, but nevertheless, we thought it would be worthwhile to do clinical trials, and we did that, and they turned out to show, they did show that during treatment with a partial agonist, this one is a partial agonist, minus triple P, we could induce get a clear-cut alleviation of the psychosis, but it didn't last. So if we went on
reduction
for
in
a number of weeks, we lost the effect again.
You got a symptom reduction in the psychosis, yes.
Yeah.
That lasted for. Okay.
Yeah, yes.
Okay. So, but this paved the way for aripiprazole, didn't it?
They started out from our concept
Yeah.
and with our methodology, and they came to aripiprazole, which became successful.
Yeah. Okay, now you want to take the concept of a milder interaction with dopamine one step further, I've understood. This is not a partial D2 agonist, is it?
No, it's more complicated, it's more sophisticated mechanism of action, very sophisticated and unique. It's a stabilizer of dopamine function. And it will be very brief in just in how complicated it. Well, first of all, behaviorally, it's very clear-cut effect. If you have animals that you put from the convenient home cage, to put them into a small cage with no interesting objectives, what do the poor animals do? They start to explore. They get an exploratory activation, and that lasts for an hour or so. But after that, they give up. They have explored everything. There is nothing more to be seen. So if you have the column at the far left there, that is animals that have been just treated with placebo, and they are not moving. Then you give to these animals in their individual, they are in individual cages, increasing doses, you get a very clear-cut activation. So the animals start to move again, and actually we know from it that actually what it looks here, it's a biphasic curve with a certain maximum, but this is a very important finding, and that what it actually illustrates, we can say already now, is an activation of dopamine neurons. They start to fire. They have stopped their activity after the exploratory phase has gone. They are lying down there, and now by means of this drug, you activate the dopamine neurons by blocking autoreceptors, and you get this activation. So this is perhaps the most important finding that we have made so far.
But then, on the other hand, it's not like a normal agonist, because a normal agonist would do this, but this is not what a normal agonist would do.
No, because if you have animals that you place into a wide, interesting cage arena full of interesting objectives, from the very beginning they have a very high exploratory activity, and if now you give increasing doses of our drug, rather than stimulating, they are doing the opposite. So you can, if you have low activity animals, they stimulate. If you have high activity animals, they inhibit.
This is a dopamine stabilizing concept.
Absolutely.
We shall hurry on we will have time for a few questions at the end, but just hurry on to the next slide, and that is, we shall not go into detail here, but these are different populations of dopamine synapses, and where do you think your stabilizer works in this?
Yeah. This is what is done here. This is Susan Cesak's picture, actually, from Pittsburgh. And what she has done by means of immunological techniques, you have some symbols here that are D2 receptor symbols. and they are blue in color. They are green.
Greenish.
They're green. These green receptors can be located in different places and have very different functions. So if you are in the synapse, where the synapse is red, in the synaptic cleft you have very high levels of the neurotransmitter, which is released from the dopaminergic nerve terminal, which is going in a diagonal through the picture here. It's released into the synaptic cleft. It's very high level, and it goes over to the opposite side of the target cell. That is the postsynaptic site. And what we think is, it would take too much time, but we think that our stabilizing drugs, and to some extent clozapine as well, they are unable to block here.
Okay.
They are unable to block. So therefore, the fundamental basic function of dopamine is spared. But what our compound is doing in other places is, here you have the autoreceptors that you have just outside the synaptic cleft, and you have a number 2 indicating on some of them the autoreceptors on this nerve terminal. And if you block them, that will stimulate the neuron. So that's why the exhausted, or that we saw the animals that were just lying there had given up, and if now we block the autoreceptors, the dopaminergic neuron starts to become activated, and that is why the animals start once again to try to explore the place with the hope of getting out, I guess. So that is a very important function. But also there are other receptors that are located outside the synapse. There you have colors that are blue, very pale blue finally, and those receptors, they are important also because they are adjusted to whatever concentration is available there. So you have a very complex interaction of different populations of receptors, and we should go for. There is a lot more to be said about this. I mean, there is also how D1 receptors come in, and also we have the cell bodies and dendrite, and those receptors there. It's a very complex pattern, but the thing with our compound is that it's doing exactly the right thing. I mean, it's a miracle drug. It's for the first time we can control dopamine in a way, in a variety of different disorders, and there are clinical studies, some of them very advanced, especially in the fatigue, which is fatigue is exactly demonstrating these activation that we mentioned to these inactive animals. There we have very good, very controlled studies showing an effect. But we have data also in a variety of other diagnoses, and so this drug has a great future.
Okay, I think this would be, thank you. I think this would be a suitable final slide, so we have time for at least 1 or 2 questions if we have got any. And I now press the question. Well, here we have a nice question from Highleg Galloway. What is your secret for success? You are obviously a very important part of the scientific community, so I was just wondering, what advice can you give us attendees on how to be so successful?
That's an important question. I think the most important thing is to believe strongly in yourself and to stick to it, stick it out. Even if people don't believe in you, if you have an idea, you have to go on and try it and work very hard. You shouldn't go on too long, because sometimes you are not on the right track. Okay. But when you feel you are on the right track, you have to go on, you have to work hard and practice to get more clever in methodology and so forth, in order to sharpen your tools.
You have always faced a lot of opposition, haven't you, for your new ideas?
Yes, they used to say what Carlsson did 10 years ago was okay, but what he's doing now is not so good. But they have been going on doing this over the century, not centuries, decades. Okay, one final question, and that would be from Don Cruikshank, and it is, can dopamine change people's predictions about their future emotional state? It's a bit complicated, but I think, yeah. Well, what I would like to go into there to mention is a very important concept, plasticity. What dopamine can do, dopamine is very important to keep the plasticity of the brain in good shape. And therefore, the future, the long-term fate of an individual depends very much on plasticity. And if you keep dopamine in a good shape, plasticity will be active, go on being active, and you can go through the phases of your life in a successful way. You can even prevent dementia.
And that is also why you think that the total blockade of the dopamine receptors may not be that good, because then you switch off this important.
Absolutely. That is what we should do is the opposite. We should really be very careful prescribing drugs that have inhibitory action, even if it's a mild inhibitory action on dopamine. One should be very careful to prescribe such drugs, especially in the elderly. And unfortunately, a lot too much is in terms of prescription of antidopaminergic drugs is being done in the elderly.
Okay. Thank you very much, Arvid. It's been a pleasure as always. And do you have any final comment?
Well, the pleasure is mutual. That's my final comment.
Thank you very much. I have one more message from the organizers here, LabRoot, and they would like me to mention that this webcast will be available for on-demand viewing through until September 2016. You will receive an email from LabRoots alerting you when this webcast will be available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. Okay, thank you very much. Goodbye.